Hey everyone, Mr. Hauk here. In today's video, we're going to be verifying some very simple trig identities as well as deriving the subtraction formulas for sine, cosine, and tangent. Let's go ahead and get started. So trig identities are equalities involving trig functions that are true for every value of the variables involved. If you think back to the beginning of the school year, when we started pre-cal, we established the following 6 trig ratios: sine, cosine, tangent, cosecant, secant, and cotangent. And towards the beginning, we also established what we called the reciprocal trig identities. However, I don't know if we called them identities at the time. So we said that the sine of an angle is equal to 1 divided by the cosecant of the angle. That's right here. The cosine of an angle is 1 divided by the secant of an angle. The tangent of an angle is 1 divided by the cotangent of the angle, and so on and so forth. Okay. We also established the following quotient trig identities: that the tangent of an angle is the sine of the angle divided by the cosine of the angle, and the cotangent of an angle is the cosine of an angle divided by the sine of an angle. Let's go ahead and verify all 8 of these, starting right here. So we want to verify that 1 divided by the cosecant of an angle is really the sine of an angle. Well, we know that the cosecant of an angle is the hypotenuse divided by the opposite leg with respect to that angle. So if I do 1 divided by that, well, we know keep, change, flip. So 1 divided by hypotenuse over opposite really becomes 1 over 1 times opposite over hypotenuse. However, we know that opposite over hypotenuse is the sine of the angle. And we can see that as we defined it right here. The sine of an angle theta is the opposite leg divided by the hypotenuse. So we've shown that 1 over the cosecant of an angle is the sine of the angle. Okay, let's do that for each one of these. So 1 divided by the secant of theta. Well, secant of theta is the hypotenuse divided by the adjacent leg to the angle. This is going to be 1 over 1 times adjacent leg over hypotenuse. However, adjacent over hypotenuse is how we define the cosine. So this is the cosine of the angle theta. So you're going to notice that all these are going to be pretty simple. Okay, 1 divided by the cotangent of theta. Well, we know the cotangent of theta, we've defined it as the adjacent leg divided by the opposite leg. So this is going to be 1 over 1 times opposite over adjacent. Well, opposite over adjacent is how we've defined the tangent. So 1 over cotangent is tangent. Tangent of the angle theta. All right, continuing in this pattern, 1 over the sine of an angle. Well, sine is the opposite leg divided by the hypotenuse. Do our little keep, change, flip. Hypotenuse over opposite. And we get hypotenuse over opposite. Here we didn't need to write that part. But if we look at that, hypotenuse over opposite, that's how we defined cosecant, which is right here. So this is going to be the cosecant of the angle theta. All right, 1 over cosine of theta. Well, we've defined cosine of theta as adjacent divided by the hypotenuse. So this will be 1 over 1 times hypotenuse over adjacent when we do our keep, change, flip. However, hypotenuse over adjacent is how we've defined the secant. So this is equal to the secant of theta. All right, 1 divided by the tangent of theta. Well, tangent of theta is the opposite leg divided by the adjacent leg. So this is going to be 1 over 1 times adjacent over opposite when we do our keep, change, flip. And adjacent over opposite is how we've defined the cotangent of the angle. So these are the very quick little verifications of the reciprocal trig identities, based purely off of how we've defined them. Okay. Now let's verify the quotient trig identities. Let's verify that sine of theta over cosine of theta is really supposed to be the tangent. Well, again, it's going to fall into a very simple argument. So we know that the sine of theta is the opposite leg divided by the hypotenuse, and that the cosine of theta is the adjacent leg divided by the hypotenuse. Well, doing keep change flip like we've been doing, this is opposite over hypotenuse times hypotenuse over adjacent. There's the flip part. Well, we can see hypotenuse on hypotenuse cancel. This is going to equal opposite over adjacent. But opposite leg divided by the adjacent leg is exactly how we defined the tangent. Okay. And then last one, let's go ahead and verify that cosine of an angle divided by the sine of an angle is going to give us the cotangent. Again, in a very similar way, let's do keep change flip. So we know that cosine is adjacent over hypotenuse. We know sine is opposite over hypotenuse. So the adjacent over the hypotenuse times, let's do the flip now, the hypotenuse over the opposite. Notice the hypotenuse cancels in the top and the bottom. This is going to give us adjacent over opposite. Ooh, that's terrible. Let's try that again. There we go. Adjacent over opposite. But that's exactly how we defined the cotangent, as the adjacent divided by the opposite. Okay, so those are 8 very quick little verifications that we can do. But now we have these identities that we can use at any time that we need to. Okay, and again, these are the reciprocal trig identities and the quotient trig identities. The next set of identities we're going to establish are the even and odd trig identities. So recall from algebra that an even function is any function such that f of negative x is equal to f of x. And what this means is that even functions, if you graph them, are symmetric with respect to the y-axis. An odd function is any function such that f of negative x equals negative f of x. And what this does, graphically, is if we plot them on a graph, odd functions are symmetric with respect to the origin. So what we want to do is we want to test whether or not each of the 6 trig values, or 6 trig ratios, are even or odd functions. And the way that we can do that is with Desmos or a TI-84 calculator. So we're going to graph each one of them, sine, cosine, tangent, secant, cosecant, cotangent, and we're going to see how they behave on a graph and determine if they are even or odd. And then what we're going to do is we're going to write the identity based off of that, okay? So let's go ahead and pull up Desmos here. This is where this will work. Here we go. All right, let's split screen it. All right, so on this Desmos page, I've actually gone ahead and pre-populated it with these equations. So let's check them one by one. Let's start with the sine. So notice if I graph y equals sine of x, it is not symmetric with respect to the y-axis. Instead, it's symmetric with respect to the origin. And we can see that because if we look at one point, for example, pi over 2 comma 1, if you reflect that point across the origin, you get negative pi over 2, negative 1. And any point will do that. Any point will work. Let's say we pick this point over here, negative 3 pi over 2, 1. Well, if I reflect that across the origin, I get to this point over here, 3 pi over 2, negative 1. Notice that simply the values change signs. The negative 3 pi over 2 changed to 3 pi over 2. The positive 1 changed to negative 1. But what this is showing us is that sine is an odd function. So if sine is an odd function, well, odd functions, if I plug in a negative input, like negative x, then f of negative x is really going to equal negative f of x. So sine of negative x should equal negative sine of x. Okay? Let's now test cosine. Well, notice that for cosine, cosine is symmetric with respect to the y-axis. If I plot a point over here, pi over 2, negative 1, then if I reflect it right across the y-axis, I get over here to negative pi, negative 1. So when you change, or when you plug in a negative input, like pi, you still get the same output, negative 1, negative 1. So this means that cosine is an even function. And what that's going to tell us is that the cosine of negative x, well, notice that for even functions, if I plug in a negative input, I get the same thing as if I would have plugged in a positive input. So what that's telling us is that the cosine of negative x is equal to the cosine of positive x. All right, looking at tangent, notice that tangent, very much like sine, does not have y-axis symmetry. Instead, it has origin symmetry, which means that if it has origin symmetry, tangent is an odd function, and that means that the tangent of negative x is going to be negative tangent of x. Moving on to the cosecant. Well, the cosecant, much like sine and tangent, again is going to have origin symmetry, not y-axis symmetry, meaning that cosecant of negative x will be negative cosecant of x. And this, by the way, should not be a surprise, because we know that sine and cosecant are reciprocals of each other. And if they're reciprocals of each other, they're going to behave the same way. If sine's an odd function, because cosecant's reciprocal, we should expect that cosecant is also going to be an odd function. In the same way here, and you'll see it here when we look at secant, remember that cosine and secant are reciprocals of each other. So if cosine is an even function, then we can fully expect secant to also be an even function. So if we take a look at its graph, that verifies it for us. Notice that secant is symmetric with respect to the y-axis. If I look at a point over here, let's say, for example, negative pi negative 1, reflected across the y-axis, you get positive pi negative 1. So we can see that secant is an even function, which means that the secant of negative x is equal to the secant of positive x. And then finally, let's look at the cotangent. We can guess, though, that since tangent is an odd function, cotangent should also be an odd function, and the graph goes ahead and verifies that. We can see that there is origin symmetry, there is not y-axis symmetry. So cotangent is an odd function, just like tangent, which means that the cotangent of negative x is the negative cotangent of x. Okay, so we call these the even and odd trig identities. And what we're going to do is we're going to use these even and odd trig identities, and they're actually going to help us derive the subtraction or difference identities for sine, cosine, and tangent. It's going to be pretty neat. Okay, so this is going to be our next part here. So we've already learned in the previous lesson, we proved each one of the sum formulas for sine, cosine, and tangent. What we now want to do is use these sum formulas in combination with the even and odd identities to derive the difference formulas. I'm going to start right here with the sine of alpha minus beta. So we want to come up with a formula that's going to allow us to calculate the difference of two angles when we take the sine of it. Okay? Well, notice that alpha minus beta is really just alpha plus negative beta. And since we can rewrite it this way as a sum, then we can use the sum formulas. Okay? So the sine of alpha plus beta, well, we know that from the proof that we did in the previous lesson, the sine of the sum of two angles is going to be the sine of the first, so sine of alpha, times the cosine of the second, so cosine of negative beta, plus cosine of the first, cosine of alpha, times sine of the second, so sine of negative beta. Now let's use our even and odd identities here. So we have sine of alpha. Well, notice that cosine is an even function, and we know that if we plug in a negative input, it's going to be equal, for example, here cosine of negative x is just going to be equal to cosine of x. So what this really shows us is that the cosine of negative beta is really just equal to the cosine of beta. No sign changes really happen. Okay, continuing. Cosine of alpha, nothing happens there. And now we get to sine of negative beta. Well, we saw up here that sine is an odd function, meaning that the sine of negative x is equal to negative times the sine of x. So if I have sine of negative beta, this is really equal to negative sine of beta. Okay? Well, continuing to simplify, we have sine of alpha, cosine of beta. This negative sign right here, this is going to turn the addition sign into subtraction, so minus cosine alpha sine of beta. And this is the subtraction formula, or the difference formula, for sine. So the sine of alpha minus beta is equal to the sine of alpha cosine of beta minus the cosine of alpha times the sine of beta. Now let's do that for cosine and tangent. So we want to calculate, or we want to derive the formula for the cosine of alpha minus beta. Again, we're going to represent alpha minus beta as alpha plus negative beta so that we can use the sum formulas from the previous lesson. So we know that the cosine of alpha plus negative beta is going to be the cosine of alpha times the cosine of negative beta minus the sine of alpha times the sine of negative beta. Okay, this is coming from the sum formulas. So going through and simplifying, we get cosine of alpha, nothing's going to change there. Remember that cosine is an even function, which means that cosine of negative beta is going to be equal just to cosine of beta minus sine of alpha, nothing happens here. And then we hit sine of negative beta. Well, we know that sine is an odd function, meaning that sine of negative beta is really negative sine of beta. And simplifying, this gives us cosine of alpha, cosine of beta. Notice the double negative here, the minus times the negative. This is going to become plus sine alpha times sine of beta. So this is the difference formula for cosine. Cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. Okay, and the last one that we want to go ahead and derive is going to be for tangent. So we're going to try to derive a formula for the tangent of alpha minus beta. One more time, let's represent alpha minus beta as alpha plus negative beta. And using the formula that we derived yesterday, well, we know that this is going to be tangent of alpha plus tangent of negative beta divided by 1 minus tangent of alpha times tangent of negative beta. Okay, so this is coming straight from the sum formula, because we have a sum now, for tangent. Let's do some simplifying. So we have tangent of alpha, nothing changes there. Tangent of negative beta. Well, we saw on the previous page that tangent is an odd function, so the tangent of negative beta is equal to negative tangent of beta. So let's go ahead and get rid of the addition sign. This is now a subtraction sign. Negative tangent of beta. All right, in the denominator, same deal. Notice that tangent of negative beta is really negative tangent of beta. Well, negative tangent of beta times this negative is going to give us a plus sign. So this is really 1 plus tangent of alpha, tangent of beta. Okay, so tangent of alpha minus beta is equal to tangent of alpha minus tangent of beta divided by 1 plus tangent of alpha, tangent of beta. And these three right here at the bottom, these are what we've just got done deriving. So these are the difference formulas for sine, cosine, and tangent. And we already had the sum formulas, so now we have both the sum and the difference formulas for sine, cosine, and tangent.